generative AI gives us a vehicle to like really improve user experiences, right? And so the first time we use these systems, you know, there's so much wow factor behind them, especially with like the newest updates from, you know, Anthropic, Google, OpenAI. And, you know, so like once you use these systems, you immediately start to think like, okay, well, this is awesome. How can I leverage this in my application? And so that's great, but when you start to actually build around these systems, it's not super obvious how to inject relevant information into these models at the right time, right? And so it's still a very active area of research. There's new types of RAG that come out all the time. There's research on measuring like token utility for like in-context learning or like scaling inference time compute. And so our research question is, you know, how do we effectively inject relevant information into these models at runtime across different domains? More specifically, how do we project search and recommendation signals into the same space that can be passed to a foundational model, given their constraints? And so that's what this talks about. Hopefully, it motivates everyone here to start thinking deeply about building these systems. You know, hopefully, it's still very new, so hopefully our community solves for them. So who, okay, so who are we? So my name is Gianni Crivello. I'm a senior customer engineer at Techolution. I'm joined with my colleague, Ethan Henley. We're part of Techolution's applied AI and ML practice. We work for Techolution solving hard problems for our customers in AI. So before we get started, I'll give a super high-level overview of our organization and what we do. So we're a services partner specializing in AI and machine learning. Some of the activities we'll do with our customers is like collaborative research. You know, you bring the domain expertise, we'll bring the AI expertise. High velocity development. So oftentimes the goal of research projects is not to keep them in you know, POC, but to actually scale these things into production. So we'll help with that. Scaling production AI and ML workloads is almost never straightforward. You know, these things are pretty complicated, and so we'll help our customers scale these production workloads. And we provide educational workshops. So kind of like the talk that we're doing right now, we'll also sponsor community events. So if you're interested in Techolution, want to talk to us, feel free to snag myself or Ethan or my CTO, and we can talk, or you can go to that email handle right there, innovate@techlusion.com, and we'll reach out to it. And so let's get started. So first, I like to set the foundation for understanding the nuances between search and recommendation, because they are nuanced. After that, we'll have a quick primer on LLMs and how they work under the hood. And then finally, Ethan will come up and we'll dive deeper into the technicals. And so we'll start with search context. So it's probably where most of you are familiar with. This is also where RAG primarily lives. In search systems, users experience what we call active intent. So where a user like knows what they're looking for, but they might not fully be able to articulate it, or it might be misspelled. That is what we would call active intent. So an example of this would be looking for tech meetups in Miami. Search systems success criteria is typically binary, so it's pretty easy to capture. Did a user eventually or find what they're looking for given a specific query? And when we start to begin to talk about search and recommendation systems, an important concept to define is their interaction model. Search systems have a query response interaction model, and they operate in the immediate time zone, right? So I give the system a search query, and I'm going to get relevant documents back, or I expect relevant documents back. So we've all seen RAG applications at this point, right? You might have a search-enabled chat application that connects to your company's HR policies. So in search mode, you might ask your chat application, hey, what's my company's policy on parental leave? The application will go and search through relevant documents, come back with a response. Going further, LLMs are pretty good at uncovering intent from a query. This is due to their internal operation that allowed them to attend to different parts of an input prompt. And so that input prompt can also be scaled across a chat dialogue, right? So in the other case, you might have an enhanced query understanding, or we can leverage these things for enhanced query understanding. maintaining a complex dialogue. A user might go to the system and say, hey, I'm looking for tech meetups. Based off of that dialogue, we might know, hey, this user lives in Miami. They're interested in generative AI. So then we're going to respond with, hey, you should check out GP Tuesdays. Now we'll get into a recommendation state, which might be a little more nuanced than we're used to. So in recommendation systems, users experience what we call passive discovery, where users don't know what they don't know, or expect the system to be proactive and curate content for them on their behalf, right? Success criteria is not as immediate as with search systems. It's more based on a spectrum. So did a user eventually watch the movie that we recommended at some point, right? Like it's much less well-defined. The recommendation interaction model is typically based off of implicit signals. So, hey, a user clicked on an item or a user added a book to their reading history. And recommendation systems typically operate off of a near to long-term time horizon, where, again, we're going to recommend something today, and we might not see signal back in a while, right? And so recommendation-powered generative AI systems, again, can be a little bit more nuanced. In recommendation mode, we might want to be proactive about where we start a conversation. So a user might go to the application and say, hey, I'm interested in learning about French culture. Based off of the fact that we know the user likes culinary arts, there's a lot to talk about with French culture, we might start with French cuisine. Or we might have rich recommendation explanations. Perhaps you're in a highly regulated use case where we want to maybe pull from a recommendation state and say, so it's the same example, but based off of your interest in culinary arts, we're going to start with French cuisine. We also might want to build proactive assistance where we curate some content based off of a user's interest. So let's say we have a bookstore and we want to allow users to sign up for an optional feature that helps users discover new books in an immersive chatting experience. And so in this case, we'll have some recommendation state. The system might be proactive and say, hey, Grant, as you requested, I've curated a list of books that you might like to read. Grant might be interested in those books and then start to converse with the system. So as a quick recap, you can think about search as like an immediate memory and with a general goal of how we can provide the most relevant information to the user as possible given the current query. Whereas recommendation is a much longer game. You can think of it as like a longer long-term memory where the goal is how can I increase the overall utility of my application over time to a specific user. Okay, so all of these are really awesome next generation user experiences. They look great, but there are technical challenges in the real world, right? And for us to overcome and understand what we're working with, we need to go deeper and get under the hood. And so my job is to make everyone an LLM inference expert in the next 5 minutes. So LLMs are performing the task of what we call next token prediction, where you might feed an LLM a prompt. For example, how do LLMs work? And that sequence is passed to the model. At some point in the model's computations, it will compute attention scores. Attention scores or an attention matrix for the input prompt. And attention scores basically just allow the model to attend to different parts of the input prompt. It's a core operation for natural language understanding. And we know that this is a computationally expensive operation. So you see the Q, K, and V values. So we'll have the K, the keys, the V, the values, and of the attention mechanism. We're going to cache those things. And so, which gives us the KV cache, right? And so anytime you see KV cache, know that attention operations are taking place. And the KV cache, just so that you all know, is an example of trading computation for memory, because the KV cache grows linearly with the input prompt. Okay, so once we perform the full forward pass through the model, we'll produce a single token. And this is the model's, what we call the first output token. Language models are autoregressive, which means that once we compute that first token, we feed that token back through the model, plus the original prompt. And you can think of this as like unrolling the model over time. So it looks something like this. And here's a visualization of it. The LLM will produce an output token, and we feed that output token plus the original prompt into the model to continue to sample tokens. The model will stop producing tokens in 2 conditions. The first is a special stop token, which basically just says, hey, you've finished the response to this prompt. The second is if you hit your max output token limit. And so these are the 2 stages of LLM inference. You have your prefill stage, which is your initial prompt gets sent to the model, and we compute this initial KV cache or this initial attention mechanism over your input prompt. You can think of this as like a cold start to the model. And then we have this decoding stage, which is the autoregressive phase of the model, where we sample output tokens and then feed them back into the model over time via time steps. And so these tokens are awesome, but where are they coming from, right? And so tokens are just simply a sampled probability over it's a probability distribution over the model's vocabulary. And a vocab is like every word or subword that the model can use to respond. And so an example of a vocabulary would be every word in the English language. And we're doing what's called greedy decoding right now, which means that we're just going to sample the highest probability, right? And so in this case, the highest probability over the probability distribution over the model's vocab is LLMs. And in this case, it's what we wanted to go for. And so at the very top, you can see the KB, which is the knowledge base. Right now, we don't know what that is. We're going to work on that in the next section. We just know that relevant information was used to get a token that we're happy with. As a comparison, without this knowledge base, which is a black box right now, we might have the model hallucinate. And so under our current decoding strategy, for whatever reason, our model sampled cats. And in a nutshell, this is how models hallucinate, right? So you have this vocabulary. We have a signal that makes the model sample something that's a bad token. And then we get into this autoregressive phase where we're now feeding that bad token back into the model. And now that's affecting the model's progress over time. And so we don't want hallucinations. We want what's happening to the left. And so that's pretty much the problem here, right? Where, how do we get useful information into the model while maintaining performance requirements? We have search context that lives in a much more immediate time horizon and a query response interaction model. And we have recommendation state that wants to build model of like implicit signals and capture higher order interactions. And so unfortunately, we can't just hack recall and provide the model with everything we know about a user because that's going to degrade performance on several metrics, right? Cost, accuracy, latency. And so to take us further into the technicals on how we would approach this problem, I'm going to hand it over to Ethan.
Awesome. Thank you, Gianni. Can you guys hear me? Cool. So we want to talk about how do we get what we need from that knowledge base? And the answer is re-rankers. So this is kind of bridging the gap between search and recommendation. So let's start off with some intuition about what ranking is doing. And there's 3 types of ranking. There's point-wise, pairwise, and list-wise. And our goal is to compute some sort of relevancy score from that. And what relevancy score looks like is usually in these 3 buckets. So a point-wise training or point-wise ranking would treat each document or vector that you're looking at independently. And each document would get some relevance score. This is more machine learning based. Pairwise would compare pairs of documents, learning preference relationships, and listwise would optimize an entire list of documents. So essentially, your re-ranker wants to take a set of documents or vectors and provide the most relevant results to your LLM. To accomplish this, there's three main goals: relevance understanding, context integration, and multi-object optimization. So your re-ranker needs to understand query intent as well as any outside context that is relevant, and then balance all of these things with business rules and objectives. That sounds like a lot, and it is a lot. It's a really cool engineering problem. So let's kind of dive a bit deeper here. We're going to get into the weeds a bit. Build some intuition about what the re-ranker is actually doing to provide this best set of results. So there's two encoder architectures here that are heavily used in most re-ranker systems, and that is the Bi-Encoder and the Cross-Encoder. The Bi-Encoder will look at a query and the documents in parallel, taking a dot product or cosine similarity to establish a relevancy between the two of them. A Cross-Encoder will take a concatenated query of your query and your document, and it's going to perform a self-attention mechanism to establish that relevancy score. So that's how it's going to work in search generally. In recommendation, you can treat this as a user item problem. So your Bi-Encoder and your Cross-Encoder are going to work the same way, but you're going to look at users and items. So you have the same architecture that's handling these two different lenses, search and recommendation. That's what we mean when we call the re-ranker the bridge between recommendation and search. It should also be noted, Bi-Encoders are generally less accurate. They perform more coarse results and are less compute intensive due to the fact you're just doing like a Cartesian product at the end, and it's built-in parallelization. A Cross-Encoder is generally way more accurate because it uses self-attention, but it's more compute intensive. So in most cases, your end users will be best served by ranking systems that utilize both recommendation and search techniques. A lot of times, you're not just doing a pure search, or you're not trying to get just a pure recommendation. You lie somewhere in between. So what we have here is a hybrid architecture showing how recommendation and search can be merged. So you can look at all the towers independently: query, user, and item. And what you do is you perform a multi-head fusion. So you perform attention on all of these independently, and then at the end, you fuse these all together to get some concatenated signal. So user actions lie on a spectrum. There's a lot of gray area between strict recommendation and strict search, and this is one of the ways that we can navigate that to provide the best and most relevant answers to our users. So kind of diving a bit deeper here, looking at some core components of re-rankers, we have an input layer, generally some cross-attention mechanism, and then that late fusion strategy. So our input encoding layer will take different types of inputs, uniformly learned through embeddings, and we kind of generalize that with token, position, and type, perform some cross-attention, computing the query, key, value interactions, trying to find those really complex relationships in your data. And then we fuse all these signals together to get some final relevance score. Taking a bit deeper look on the attention mechanism, this is really where some of the magic happens when it comes to kind of getting these attention outputs. We start with some input embeddings. You have your QKV, it keeps coming up, query, key, value, perform a scale dot product and a softmax normalization to get that final attention output that you can put into that late fusion layer. That fusion layer, this is a pretty big generalization because this is where a lot of the engineering happens. Most recommendation systems or ranking systems kind of follow the first two steps the same way. And then this third step here where you fuse your signals and try to customize it to best serve your end user is where you're going to do a lot of the engineering. So generally, you have a query, a user, and then some relevant context, and then you dynamically generate some weights based on what signals are most important to your context. These signals are generally concatenated at the end to get some final score. So this all kind of comes together to create something we call a relevance space. So we start with your search signals. This can be BM25, it could be some neural match, it could be click-through rate, whatever search signals are important for your application, and then we normalize them. Whatever mathematical application makes most sense for your specific signal, so it could be like a logarithm for BM25 or whatever. You normalize that signal, and you can do the same for your recommendations as well. So maybe user item similarity is really important on your recommendation side, and you'll normalize that. These are then put through, we call it neural mapping, but it's a neural network that allows you to perform some multi-layer transformations. You take these signals, put them into a dense vector, and try to scale it down so that you can perform a sigmoid operation again, giving you a result between 0 and 1 for how relevant this particular concatenation of signals is to your user. And this kind of relevance space is where you bridge the gap between your search signals and your recommendation signals and get really rich and relevant results for your end user. And now we're going to do a quick case study to contextualize this a bit, because it's kind of up in the air right now. What is this stuff? So we're going to do a case study on a paper called RecSys, Composable Learning to Rank using JAX. JAX is a popular deep learning framework developed by Google DeepMind. Hopefully this will help us contextualize that relevance space problem and show another approach to looking at it. So some quick motivation behind this paper. Essentially, when this was published, learning to rank or ranking systems was still pretty new. There was really only 2 libraries that dealt with this, called TF Ranking and XGBoost. They had a lot of problems. They really weren't good for production, and a lot of production needs exceeded the capabilities of those libraries. So researchers at Google DeepMind developing JAX decided to add some native support for ranking systems. Particularly well suited because JAX is a purely functional kind of paradigm, which means that you can create your own composable ranking functions. So how they kind of create that relevance space or unified ranking space was using only math, really no real neural approach to it. So given a search signal and a recommendation signal, they convert those ranking metrics to some differentiable form, create some boundaries for some optimization to occur, and then enable the exploration of that created search space where we can run those composable functions. So like what we showed, this allows for the combination of search and recommendation signals. So there's some differences between what we show at the bottom and the RACS approach in the paper. So it really comes down to how we want to solve the challenge of combining disparate ranking signals. The neural approach treats this as a learning problem. We want to learn the mapping from various raw signals into some unified space. RACS, by contrast, takes a math-first approach, constructing transformations through some approximations that preserve the ranking properties. So both approaches recognize that bridging search and recommendation is really important, and it kind of creates a common language for your different signals. They just differ in how we create that common language. Production re-rankers usually leverage both, so some mathematical approach first for efficiency, and then a neural approach later for really good precision. So that kind of brings us to like re-rankers in practice. What does this look like in production? How does this kind of become a bit more contextualized? So what does a re-ranker in production look like? So there's generally 3 distinct stages. You have some candidate generation first, where we have a huge knowledge base of tons of documents, and we want to generate maybe 1,000 of the most relevant, and or 10,000 of the most relevant through some search that's really, really coarse. We then kind of go back to what I was talking about earlier, where a Bi-Encoder will coarsely reduce that 10,000 to maybe 1,000. That gets us some more relevant predictions. And that's the more math approach. It's super quick and not very compute intensive. And then when we have those 1,000, we'll break that down into maybe 100 by using that cross-encoder. We refine the candidates to a very, very small set of the most relevant predictions. So generally, early stages, you want to look for speed. Later stages, you want to look for accuracy. And every re-ranker system is going to be different, but generally you'll follow these kinds of steps to try to get your candidate size to the most relevant. So how to train your re-ranker? It's a pretty difficult task that requires the engineer to know how they want to manipulate those 3 main loss functions to best interact with their data. So generally speaking, your data is going to be clean, sampled positively and negatively, so you can get some really good data representations. And then you will compose the point-wise, pairwise, or list-wise functions to dictate how that training data is going to contribute to the overall purpose of your model. All these losses, or your composition of losses, will contribute to your gradient updates. So like in any AI system, your loss is a really critical factor to defining how it's going to work. So let's maybe spend a little bit more time revisiting those loss functions again. So in production, you really have a few choices for each of these. For point-wise, generally, more machine learning based, you do MSC laws, binary cross-entropy regression. Pairwise, you have options like hinge laws, RankNet, or lambda rank. And then for your list-wise, you have ListNet, ListMLE, and approx NDCG. These all kind of have different uses depending on your specific use case. You would choose one or the other. But generally, these are your options to try to generate those signals so you can train your model to perform the best. Now, what do we look for in production? It's really easy to kind of get caught up in all that architecture stuff. So like, what metrics actually matter here? So first, kind of broke it into 4 categories. Again, there's probably more in some use cases and less in others. But generally, latency and performance are going to be pretty important. So each stage in that re-ranker architecture is going to have some latency budget, most likely, and together they'll have to stay under some P99 requirement. For ranking quality, so how do we measure if our re-ranker is actually performing correctly? We have traditional offline metrics. So you have NDCG at 10. NDCG stands for normalized discounted cumulative gain at 10 queries. So that measures the ranking quality with position-aware weights. So a perfect, re-ranker would have 1.0, and so we're looking at maybe 0.8 as a pretty strong performance. The at 10 just means 10 queries. Usually your user isn't going to go past that, so that's really all we care about. But again, that could be dependent. Your MRR, mean reciprocal rank, is critical for tasks that require you to find the right answer, so kind of needle in the haystack kind of testing. So a 0.6 means that on average, you're going to have a good result in your top 2 positions. Your precision at K will look at the fraction of relevant items in the top K results. Doesn't really consider any of the ordering there, but it's kind of a more general approach to find many relevant sort of scenarios. And then lastly, you have some mean average precision, which is going to look at precision in relation to your ordering. So that's a pretty good indicator for real world performance. And then, of course, you have like system health. You're going to have some restrictions on your GPU, cache hit rate, error rate, QPS, TPS, et cetera. Excuse me. They'll help us keep the latency where it needs to be. And then finally, business impact. So how are you going to convince your boss that, hey, we need a new and sophisticated re-ranker system here? These systems don't live in a vacuum. So it's really important to measure things like click-through rate, session length, bounce rate, and conversion rates, which are pretty critical metrics to justify the engineering resources needed to develop a really sophisticated re-ranker. And so I kind of just want to bring it all together here to kind of go back to what Gianni was telling us. So re-ranker stuff is great. Where does this actually fit in the LLM stack? So let's look at this diagram here. We saw Gianni walk us through earlier. LLMs operate in a search space to find the most next relevant token. However, he mentioned that the knowledge base is really critical for finding that next relevant token, and it acts kind of as a black box. So how does that knowledge base give us the high activations for the tokens that we really need, and so we can avoid hallucination? That is where the re-rankers kind of fit in this. This is kind of where everything connects. So by enhancing our knowledge base with a really great and robust re-ranker architecture that's made to help out our end users, we're fundamentally improving that search process that allows our LLMs to generate the best possible candidates. At the end of the day, this isn't just about making LLMs more accurate, it's about making them more personal, more contextual, and ultimately more useful for real-world applications. We're giving LLMs the ability to not just know what might be relevant, but what might be relevant to this specific user at this specific moment. And I kind of want to leave it there. Any questions from everybody about this? Hopefully this gave you guys a pretty deep dive to a relatively niche but really important part of the LLM stack. That's critical for your end performance. Thank you all. Sure. Yeah, come up to the microphone if you got any questions. Happy to.
I go on. Thanks, guys, for the presentation. My name is Will. So it seems like the re-ranker is using essentially traditional ML to then improve the LLM. Have you used an LLM to improve a ranking algorithm? Have you seen architectures like that?
So the re-ranker is pretty important for helping the LLM figure out what the next most relevant token is. So if you're familiar with like retrieval, augmented generation, or RAG techniques, you might have your own knowledge base for the LLM to talk to, or try to get some personal information into your LLM. Generally, the re-ranker fits there to try to help your LLM get the most relevant tokens out of it. So it's kind of it acts more of a support for the LLM. Are you asking more of like replacing like the LLM search with another LLM?
Yeah, I'm actually mostly referencing that slide that you had with XGBoost and sort of the re-ranking algorithm doing better than sort of traditional rankers. Where
towards the end.
essentially the question is, can you switch around the architecture and make traditional ML better ranked using LLMs?
You could. You potentially could. So LLMs are also expensive, right? And so the point of having like a lightweight re-ranker is to keep, it's to improve token utility, really, right? So yes, you could use an LLM or a variant of a language model to help and assist with re-ranking. As long as you had those loss functions that were mentioned earlier, you could backpropagate through them and train a custom language model. Yeah, absolutely. Again, though, bigger the model, more compute, more expensive, slower.
Makes sense. Thanks.
Yeah, thanks.
Thank you for the presentation. Very interesting. How do you plug this in? I mean, unless you're OpenAI or Claude, how do you have access or even the use for this? Is this, like, for example, websites have a search. They could do so, much more using something like this, but they don't run LLM. So just trying to understand what, is Algolia, for example, something that uses a re-render like this?
Yes, yeah, absolutely. So the question was if Algolia uses a re-ranker. I mean, I don't work for Algolia, but I'm certain they probably do. The trick here is projecting the search signals. So all of like that, what you're talking about, what Algolia does is search, projecting those search signals and recommendation signals into the same space that we can connect a language model to.
And how do you do that?
From what perspective? From a training perspective, or from like an engine?
From like a practical. I mean, who are your clients?
Okay, good. So great question. So who are our clients? Again, when we use these large foundational models, it's not super clear how we would inject information outside of just retrieval, right? And so where we would engage something like this, I mean, like re-rankers, if you guys are building generative AI applications, they're very common. What we're proposing is that by fine-tuning them a little bit more and exposing them to like a different domain, which is recommendation, you can improve re-rankers, right?
Yeah.
Which can help. It can help. In terms of training, I can absolutely take it offline and tell you how to do it.
All right. Thank you very much.
Thank you.
I appreciate the presentation. Thank you for sharing all this information. I'd love if you could share the slides in the Telegram afterwards.
Sharing the slides on Telegram? Yeah, absolutely.
Yeah,
I'll do it
yeah.
right now. Yeah, after this.
Yeah, cool.
Cool.
Yeah, 'cause it's like, it takes some time over. Thank you.
Absolutely. Thank you. Any other questions?
Yeah, thank you so much. So, I was, kind of handling some, also some stuff with the crowd, right? Audio, visual, and stuff like this. So, but one of my questions that, stuck out to me is, you have this part where you essentially get the first 1,000 candidates, right? You filter that down, and then you get down to, you drill down even more to get the most optimal of those few. So what is the trade-off between, getting the right let's say, candidates and speed. So for example, drilling down, what kind of speed are you looking for? Are you trying to get this done in as fast as possible response, or is this also for, in a conversational setting, or is this for any type of system? So for email, for example, you might be able to drill down even further, I'm guessing, right? And to get the perfect candidate, and so therefore you can spend more time. But if you're doing it in like a chatbot setting, then maybe you need to do a less filtering, for example, because you'd have to, so would that be kind of the thinking in terms of getting the candidates? I'd love to hear your response.
Grant, really good question.
Thank you.
Do you want to take that?
So yeah, depending on your context, there's tons of ways to go about this. Generally, you want the best possible speed for your end user. So what we try to do is try to handle the bulk of the candidate sets from, maybe you start with like 1 million. And you want to get that down to 10,000. You're going to try to do that in the coarsest way possible because generally, there's not going to be many, there's only be a few relevant things. So if you can find those signals really quickly, then you can just get like 10,000 of them, bring those in, and then we can drill down from there. And that can be done really quickly. That's why Bi-Encoders are really helpful.
Right.
Or the JAX numerical kind of approach. Generally, you do want to look for speed. So the best you can do with like the coarse Bi-Encoder, the more you can drill down from there, the less your cross-encoder or whatever precision part you will actually need to use. So you can get a lot quicker from there. So if you can get like maybe 100 from 1 million really, really quickly, then your cross-encoder doesn't have to do much to get that 100 down to 10, and you have a really quick system from there. And that's a lot of just kind of architectural approaches that you have to take depending on whatever that context is.
Amazing. Thank you so much. Really appreciate it.
Grant, it's also helpful to understand like what's fast and what's slow. So that's really fast and that's really slow.
I see.
Yeah.
Interesting. Thank you so much.
This happens in parallel, right? And this can
Right.
also be hierarchical, right? So you can have like 1 million retrievals and then like filter them through some hierarchical, like, million, and then have that do again to 100, then to 10, and then run the slow thing. That's also
Right, makes a lot of sense, right? Because when you're handling numerical, it's going to be much faster for the Bi-Encoder, and doing it through the right side will be slower. So thank you so much for answering my questions, and if anyone else has any more questions, feel free to ask, and thank you.
awesome. Thanks, everyone.